Okay, so I have this really bad habit of changing slides until the very last minute before I go to class. Normally, when I actually goes to real class, I have to stop some number of minutes before just to run to the class. Here I'm here. So in fact, my iPad says class is starting, suggested location, the home address, because that's where I'm mostly sitting. So what that means is that I just basically completed everything, and then I had to actually get the link and get on. Anyway, um, so only today and the last class is on December sometime, right? December 6th, is it? Um, when are we? No, December 4th is the last class, right? Okay. Um, so couple of announcements before I go forward. I'll send you an email again, but the one thing, so basically there's no class next week. You know, it's Thanksgiving weekend. So we'll be meeting 2 weeks from now, which is for the last class. And what we'll do before that is I will send you sort of an interactive, we'll try to do interactive review in that last class about things that you got out of it. In preparation for that, actually, all of you, I normally do this for each of my classes, so I'll do it here too. I will send you like a questionnaire that each of you will basically write your comments for that as a comment on Piazza. Okay, so it would be things like 3 things that you got out of this class, 2 things that were surprising to you, that sort of stuff. Okay, and if basically it'll also give you a chance to remember what happened. I understand there was not too much pressure and it was only once a week. So some of you probably took it a lot more seriously than others. But either which way, I think the note summaries give a sense of what happened in each class. I know some of you are actually writing it, by the way, it actually becomes quite clear as to who is writing the notes and who is not, because I keep getting these updates when things happen. But I think several of you took that seriously. But the rest of you, if you forgot what happened at a different certain classes, then you can just look at it and then answer these questions. It would be typically like, let me see if I can remember what happened in last. Yeah. So for example, my intro to AI class, I had things like this. Part 1, list 5 or more ideas about AI that you appreciated over the course of the semester. Part 2, list 3 or more non-trivial technical details. Part 3, list 2 or more ideas that transcend AI. Part 4, list 1 or more idea that you wished we discussed more in the class. This is the kind of thing. Okay, I will adapt it to our class, and then send it to you. And you would then respond to it as a comment. Remember when the class started, you introduced yourself, each of you had a comment, just like that you would do it again. So in fact, you looking at what those also gives you a sense of what actually people got out of it. And I think that would be a good way to sort of summarize what happened. And of course, I'm sure there may be more things we'll bring up in the last class, but this would be one thing that you would have to do before last class. And I might well, depending on how things go, we might well actually have you bring up some of those things that you've already written in front of everybody, but we'll decide that separately. So that's regarding, so that's sort of like a required assignment. So there was a question by one other thing. Generally, I sort of probably didn't make it as clear, but in general, I think you could meet me. You could have asked for meetings to talk to me about anything you wanted regarding AI. you probably didn't have that much of a reason for now, but certainly one of the ideas is, I know your faces, you know my face, okay? There is this thing, actually, I'll send you a link, that sometimes, especially for freshmen among you, universities are huge, especially a state university like ASU is extremely huge. And it's very, very easy to get lost in the shuffle. And so, you know, for the 20 or so of you, essentially, you know my face, and I will remember that, and that we spent, you know, 7 classes here. Basically, whether during now or later, you can always come back to me and ask me questions that you think I can help with, and I will respond to you. Okay. This has been said to be, that's sort of the usual reason I would think to do a freshman seminar, so that you will get to see, you know, somebody, and you'll have a potentially better connection than just some link on the web page. Okay, that said, there was a specific question somebody asked about what other courses to do in AI, if you know, afterwards, etc. I basically can answer part of it right now, but I mean, in general, those sorts of things, you know, regarding AI courses, there are just several different ways you can get to this subject, you know, as we have looked at here. The technical electives in computer science, mostly the main course that you should take is Intro to AI 471. And to get there, you should have had good background in discrete mathematics, in linear algebra, in code, in programming. And in computer science, they'll also expect you have like data structures background. You know, so those are the things that you're supposed to have to be able to do 471 in computer science. There are several, and within computer science, which I'm much more familiar with, you can, most of the AI related courses come at the 4th level, level 4, that means senior level courses. So typically people wind up taking them in their junior year, you know, or senior year. That's what winds up happening. And I normally tell people that one thing that you may want to remember is, so the courses essentially have partial ordering in any major that you are in. You know, some courses have prerequisites, some other courses, right? There's basically, so it's sort of a directed tree of courses that you have to traverse to get your degree. People tend to go breadth first. And in fact, that's what your advising office will tell you. They'll tell you, do all the 1-level courses, then do all the 2-level courses, then do all the 3-level courses, then do all the 4-level courses. I think that's not necessarily the only or the greatest idea for undergraduate study. If things that are more interesting to you, you should try to take 4-level, 3-level courses in those areas as early as you can, okay? Which will require that you traverse this prerequisite tree in a depth-first fashion. The idea is go as, you know, the things, you know, you look at the area courses that you are interested in and specifically see what are the prerequisites that you have to have taken to be able to take those courses and do them earlier. That's something that you might be interested in doing. But, you know, in CS, in addition to 471, there are other 4-level courses. There tend to be more 494, which are like special topics courses. There is a 494 machine learning course too, that's available in CS. That's in the CS level. In other areas, I think statistics, they have data science major, and they have some courses there too that might be relevant too, in terms of, I don't have as good a background on what courses they're currently offering, but that's the other thing that you may be able to do. There may also be courses on like things like AI and ethics, but that would be typically in the school of, I guess, SFIS, School of Innovation and Social Change or something. That's the one that winds up having those kinds of courses. Oftentimes, unfortunately, some of these wind up basically being accessible only for 4 level or higher. So to some extent, that's what you got here. At least some of the aspects of this subject you get a sense of right now before you wind up taking them more in a more traditional format in a course with exams and so on. Okay. I think Gordon is the one who asked this question. Is he here? Are there any other things that I can say about these courses or what to do after? If you have other questions on these, you should be able to ask them on Piazza too. But if there are any questions that I can answer right now, bring them up.
I have a question.
Okay.
So there's another class about AI, which is like NLP, right? So would you recommend us to take intro to AI first and then NLP, or is it like okay to take?
So there are, basically there are no NLP courses specifically at the undergraduate level in computer science department. There are in there is the 5-level NLP course. Intro to AI doesn't often get all the way into all the topics. I mean, the Intro to AI textbook is pretty big. Actually, this is not even this is the second edition of the textbook. You can see how thick it is. And there is a 4th edition right now. And I teach from this, and it has everything, it's basically, it has all the topics at the Intro to AI level, but really it needs to be a 2-semester course to cover everything. Instead, an NLP course will just directly introduce NLP without actually having talked about how all the other pieces fit. But we don't currently have any undergraduate level course, as far as I remember, in computer science, at least. Okay, you can, if it is available, it will be available as a 4-level course, and you can take that without taking Intro to AI. There is no prerequisite structure between them. Okay, so you can take like a machine learning course, an NLP course, and without taking the Intro to AI course. Intro to AI, I think, is actually a much better idea to do that too, because it will give you a sense of how things fit. But if, for example, if you're interested in NLP-ish things, linguistics department might have some courses that might be actually available for undergrads. So the trickier aspect for some of these courses would be whether they're available for undergrads or not. And that's just, it's not that it's that hard a material, it is just that on the catalog, there may not be those courses available. Okay, but if they're available and if you're taking it, you can take them without taking first 71. Other question?
Yeah, for those of us who are not, like in computer science or don't really have a big background in coding, what kind of things do you suggest that we could do to like deepen our understanding of AI? Like any
Speak louder, please. You're trailing off. Go ahead.
Sorry. For those of us who aren't, into computer science or aren't really have a big background in coding, what kind of things can we do to build off of our knowledge and interest in this class?
So there are 2 kinds of knowledge, right? Obviously, one is the conceptual knowledge of what are the big topics and what are the actual trade-offs in doing machine learning or doing sequential decision making, which we were talking about last class, for example. That essentially, many of these topics were done outside of AI. So in fact, there are just so many areas that are all basically that have all just sort of become AI now. Okay, it's become AI to some extent, even though I like it and I've been, considering myself as somebody doing AI for my entire career. I do realize that essentially many of the problems that AI researchers look at have been looked at in other areas and other departments already. So for example, there's an entire area called operations research, which many, you can either get it in mathematics departments or the business schools, and they wind up talking about decision making, and that's connected to planning and decision making in AI. There's an entire, which of you, if any, are in electrical engineering? Mechanical engineering people, there are some, and there's control theory in mechanical engineering. Control theory essentially is about how to control the behavior of an agent. Okay, so to some extent, actually, some pieces of these have been done in, for example, computer vision was done for the longest time in electrical engineering departments under the name image processing. And they were there way before, basically CS folks got interested in computer vision. And one of the other interesting things is that to do image processing in general, having background in signal processing helps quite a bit. And that's not just coding. So as much as I'm in AI and I'm in computer science and I want to push those, but I think that's not necessarily, it's the problems that matter. It's not the department in which you looked at those problems. Okay, so for example, if you wind up taking courses in signal processing, courses in random processes, courses in statistics, they're all going to be relevant when basically you can just call yourself an AI guy at some point of time. Do you understand what I'm saying? And one of the interesting things is coding is important skill, but the entire computer science as a whole has been trying to make coding easier and easier for lay people who don't have a huge coding background to still be able to do. In fact, today, one of the things I'll try to do, and I have a long list of things I was hoping to do. One of the things I wanted to show you is this Tensorflow playground, which basically, Tensorflow is already a high-level language in which you can actually, write, basically write code to kind of train larger sized neural networks. But basically what they'll wind up doing is they'll make many of the things that you would need to do as library routines, so that as long as you have almost a conceptual idea, you should be able to get started to some extent. I'm not saying this will give you the same level of the coding efficiency as somebody who spent all their time actually going from bottom up. Like if you do in computer science, you'll actually start doing, assembly language too. You do computer architecture, you do systems organization, you think about operating systems, you think about a whole bunch of things before just doing the coding. But people in data science just basically get to some package directly. They'll either look at R, or these days they're looking at like TensorFlow, etc. Data science turns out to be like a very popular area, especially right now. There's tons of jobs there, etc. It's basically data science is statistics. Do you see what I'm saying? So I think it's not as important. I mean, it's not as important that, and in fact, even now in computers, in AI, researchers working in AI, or even practitioners working in AI, come from many, many different backgrounds. To some extent, it's actually a cynical way of looking at it is that somebody, there was an old story that people, much of Bell Labs. How many of you have heard of Bell Labs? AT&T Bell Labs. So, basically the phone company, the Marble basically was, it had a monopoly and it had tons and tons of money. And one of the advantages of having monopoly is that they can just spend a bunch of money on basic research. And some of the greatest inventions of the 20th century have happened in Bell Labs. Transistors, which basically semiconductors, devices, were invented in Bell Labs, for example. So one of the interesting points about Bell Labs is that it used to be said that AT&T and Bell Labs would hire any physics PhD, even though they are not really doing physics in phone company. And their idea being that if you're smart enough to do physics PhD, I'm sure you're smart enough to do whatever we needed to do. Do you understand what I'm saying? So a lot of people essentially do whatever it is that they want to do, and then basically just call themselves AI right now because AI is where all the jobs are. And so that is actually true in most of the, some of them are pretty impressive researchers. Their backgrounds are not computer science at all. Okay, and that's not just the older people, it's also true for very new people coming into the area, because data science as a whole is just statistics plus computing. Okay. But I mean, the thing that I can tell you is some of these questions, you may not even know how to ask these questions right now. But what I can tell you is, if you ever send me an email asking me, I get a whole bunch of mails, but I will make an exception for you guys. If you send me an email, basically identifying yourself, if I forget your name, identifying yourself as the person who took, HON294, and you have this question, I will try to get back to you to the extent I have the knowledge. And certainly that is something that you can imagine that is like a perk you are getting for having sat through this course. Okay. Anyway, that my email, you guys know, rav@asu.edu. As long as I'm at ASU, that would be my email. Anything else on this direction? You can still ask any additional questions about this. It's a very reasonable thing to ask, and you can ask them on Piazza, and then I'll get back answering them. Anything else?
I have a question. It's not really related about this topic. It's just about AI in general. Yeah.
Mm-hmm.
My question is, in the video we watched of your last lecture, you were talking about, and in last class in general, we were talking about rewarding AI for exploration. And like one of the problems is deciding how long you should explore and stuff. But my question was, can you go into more detail about how you would reward an AI for exploration?
No, I mean, essentially, so what you essentially, the agent has to do exploration. When you're doing, when the agent is doing exploration, it's not getting necessarily as much reward at that point of time as exploiting its knowledge. That was the point I was making. So this part of the map, and you know how to get pretty good rewards by just using the best policy with respect to this part of the map. Looking for the rest of the map, there are no guarantees that when you're looking at the rest of the map and you explore, this is actually true in general. Statistically speaking, going to school is a waste of time, right? Because remember, all pretty much the entire billionaires, they all apparently just dropped out of the college. So in fact, one of the important prerequisites for making a lot of money is to drop out of college, right? If you go with Bill Gates or Mark Zuckerberg, etc. So in general, it's not that you can prove that exploration will always improve your reward. And certainly it won't improve your accumulated reward in temporarily, in the sense at the time when you're exploring, you may not necessarily get any extra reward. Okay. But even in the longer term, it may not. So in fact, this actually brings up this very interesting question. In the long, but so first of all, statistically, if you explore of the world more, like for example, the reason we even have colleges is, statistically speaking, people who go to colleges seem to have more opportunities open to them. Okay. And that's only statistically true. There are, I can always come up with an example of my friend's co-worker who dropped out of elementary school and started like some big company and is making tons of money. Okay, but statistically speaking, it's like, it does look like there's more to the world, and most people are better off exploring beyond elementary school. But should you explore beyond undergraduate level, beyond undergraduate level to do graduate study, and beyond graduate study to do PhD, beyond PhD to do postdoc? Okay, at that point, it becomes more and more of a thing there. You actually have to have, you should experience reward just for exploration. So one of the things that people do is, we essentially sometimes get pleasure from the process. Do you understand what I'm saying? So, and I think this is what I was saying last class, that to me, I mean, I think of the world from the point of view of AI, and I think of, when I see somebody, the most important thing for me is, what is their reward metric? Because first, let's point out first that in that little grid thing, we put some numbers and said those numbers are the rewards, right? Actually, so instead of numbers, you can put money as reward. But the reality is that reward for people is only dependent on these things. Do you understand what I'm saying? Some people actually don't care about money, at least certainly beyond a certain point. And basically, so what you get happiness, essentially, is very much personal to you. I can't tell you that you should be happy because you became a millionaire. You may well become miserable sitting in front of, your $1 million and sort of, securing them, 24 hours a day. So your reward metric really is both your personal reward plus some external things. Do you see what I'm saying? So this is why actually there was a whole entire discussion that was going on last weekend, and this happens all the time. Who should do science in general? You should not be doing PhD, for example, because you think at the end of the PhD, you'll get a Nobel Prize. First of all, even Nobel Prizes, it's only a couple of $1 million. You can make billions of dollars by dropping out of elementary school and starting some tortilla factory. If yours is the best tortillas, you will be billionaire. You don't need to know anything else. Okay, you probably should be doing PhD to some extent, at least, because you like the process. So you're getting reward by staring at the computer and writing programs, staring at the books and reading about these arcane things. If that's not you, you shouldn't be doing it to some extent, because eventually you will be miserable. Okay, so so to some extent, we, in some sense, create our own rewards, because it's based on our personalities. Okay, and we are doing exploration in life. You do exploration because you are not too happy with where you are, and you're hoping that maybe doing this will get you a better return, or in fact, you enjoy exploration for the exploration's sake. Most scientists, that's exactly what they do. Do you see what I'm saying? You can't tell them you should not be enjoying it. I can't tell anybody you shouldn't be enjoying it. That's like the stupidest thing to do. We enjoy what we enjoy, right? And so that's why I find that when I see somebody, my first question is not what are their capabilities, but what are their reward metrics? What's their reward metrics? What makes them happy? Because we will do things that will make us more happy. And we more or less have similar capabilities. You know, we tend to make a huge difference about, oh, no, I can do 15-digit multiplication much faster than this other person. But really, we are more or less similar in capabilities. What differentiates us, to me at any rate, is, you know, what is your reward metric? Okay. And the exploration essentially will be, you know, sometimes exploration might become part of the reward metric. In fact, there is this whole entire thing connected to this about incentives. You know, you basically give an incentive to agents to behave in a certain way by providing them rewards to behave that way. Okay. And there is this whole entire area called incentive design mechanisms, basically are what's called reward shaping, where if I know what you like, I can make you do what I want you to do just by essentially ensuring that you will get your kicks. Do you understand what I'm saying? That's what, you know, my example of this is, you want to send Homer Simpson to library, which he would never, you know, you guys know who is Homer Simpson, right? So he'll never do if his life depended on it. But if I put a large number of pink donuts between here to the library, he will, you know, basically follow the trail of the donuts and find himself in the library. So that's, to me, reward shaping. I just, without pushing him to the library, I made him go into the library because I know he likes pink donuts. Okay. So to some extent, we act as if in MDPs, we assume that we know the rewards. Okay, but we should really know what is the reward for people. We really need to know what is their personal reward structure. There are generally, most people like some money. Nobody really wants to live without a, you know, like a roof on their head. But between that and having like huge compounds, you know, Malibu Beach, there is a large amount of, you know, spectrum of variation. And some people basically might say, as long as I have a roof on my head, I would rather spend my time reading instead of, you know, making money to make this huge big house. That's their reward metric.
Can I?
Okay. Yes, please go ahead.
In one of my, like, I'm a psychology student, and we were talking about motivation and like positive psychology and industrial psychology. And there's this large scale study done by these economists at Harvard, and they were doing it on motivation in the workplace. And I think it was done on like a bunch of engineers within a company. And so they had like the project managers tell the team of engineers to like build like their like most desired like product ever. And so then the engineers like built it, and then they would give them money, and then like they kept on building things more and more, and then kept on rewarding them with money. But at a point, like the people stopped like caring about it, because like they would pay them, but their boss wouldn't listen to them. Like when they would pitch the idea, but like they had the other group that they told them to like keep on building things that they like really loved. And instead of them getting paid for the models they kept building, their boss just like listened to their pitch and just like gave them feedback and just responded and reflected with them. And then they felt like much more like motivation and happiness within the workplace. So just like playing off the point of like money, like in your job does not motivate you. It's like,
no, yeah, no. So it's pretty well known that, first of all, we just use money as like a reasonable, it's like a reasonable substitute. Economists certainly, even economists realize that money is not money. Okay, most economists now start talking about well-being in general. Okay, but the point is, money is quantitative, so it's easier to kind of throw money at people. But it's completely understood that what makes people happy, first of all, is intensely personal to them, and secondly, it's not always just money. Even given the fact that money can money is fungible. You can convert money into other things that you want. Okay, for example, the usual thing is I'll get the money and then I'll convert it into what else I want to do. Except if you're working 80 hours a week, there is no more hours left in the week to do the other things you want to do. Okay, so there's always these conflicts in general. It is quite well, it's a very good point that we will use reward as if it's a quantitative number, but what is a reward for people is obviously like a harder thing to actually evaluate. So in fact, as I said, I mentioned that paperclip, even if I'm trying to give you the right help exactly when you need it, if I have a smug look on my face when I'm giving you help, you get mad at me. Do you understand what I'm saying? You shouldn't. You really should say, if suppose one person is going to give you the right help with a smug look, the other person is going to give you the wrong help, but with a lot of sympathetic, oh no, it's going on like this in your life, etc. At a certain rational level, we should say, I should go with the smug guy because that guy is actually giving the right help. But we are what we are. We basically, evolutionarily, we don't necessarily like people with smug looks. We feel like punching them. And so we will basically do what looks like irrational. And in fact, the word rational versus irrational is actually defined. One of the very interesting things that actually this discussion brings up, and I hope somebody reflects this in the summary, is words like reward, words like rational. Okay, these are not objective. Objective means the entire universe agrees as that this is a high reward state. What may be high reward state for you may be low reward state for somebody else. Do you understand what I'm saying? So the issue then is that you are allowing for personalization. You just what is rational? So what is irrational is with respect to your reward metric. Do you understand what I'm saying? Suppose you, and I'm just generically showing you on the screen, like money, and I like books, just reading books. And you make actions which seem to be mostly getting you to spend time in library with no money coming to you. And I seem to be spending all my time making money rather than reading books. Then you are irrational, I am irrational. Do you understand what I just said? It is irrationalities with respect to your reward metric. Okay, to throw that even crazier, you would say the reward is personal. That's fine, I understand. Okay, but what about something like probability? Like in that MDP that we looked at last class, there is reward, which I said now is personal. But there is also this idea that if I go up, I go 80% of the time up and 10% right and 10% left, right? Remember I said that those are probabilities. Okay, it turns out that in general, you would think the environment at least is objective. That means everybody should basically look at the environment the way it is. It's an objective reality beyond us. Okay, whereas our rewards are subjective reality for us. Okay, turns out that in probability theory, there is this whole entire area called Bayesian probability. How many of you heard the word Reverend Bayes' name? Bayesian probability essentially is you can make personal probabilities. You can make personal probabilities. Okay, and then, so you can have personal probabilities, you have personal reward metrics. Then when I say you're irrational, it's only irrational with respect to your personal probability and your personal reward metric, you still are not doing the best actions with respect to them. Do you understand what I'm saying? Okay, so the requirements are that you be consistent with your beliefs and your rewards. Okay, that's what the theory is going to tell you in terms of being intelligent. Now, of course, why the whole interesting thing about Bayesian probabilities comes in because actually you always assumed, right, that in grade school, in high school, when you heard of probabilities, you thought of probability as a ratio of an experiment that was done infinitely often. And the numerator is the number of times the experiment came up in one way, and the denominator is the total number of experiments. And that ratio is the probability of that event, right? Okay, so my question is, what's the probability that in 1922 on November 2nd at 4 o'clock, Einstein was having a cup of tea? Did you just understand what I asked? Do you feel like answering that question or not?
Are we supposed
It's
to
like
have
a
like a
reasonable what? I'm sorry, go ahead.
is this a rhetorical question?
No, it's not a rhetorical question. My question is, for these kinds of things, would you feel like there's a probability or not? Would you think the probability would be 0?
No, couldn't you?
So my point is that I asked a question, a probability question. You are almost willing to give a number to it. But if you really believed that a probability is essentially an asymptotic ratio of an infinitely repeated experiment, you should say, you should not ask me this question. This cannot have probability. Do you understand what I'm saying? Because you cannot make November, whatever date I said, November 2nd, 1934, at 4 p.m. happen infinitely often. Right? You can't actually tell whether Einstein and how many, if you can happen, make it, it's like, what's that thing called, the Groundhog Day. If we can have a Groundhog Day scenario, November 12, 1934, 4 p.m. can be repeated infinitely often, then you can check how many of those times, of those days, Einstein was drinking tea versus not drinking tea. And then you can give a frequentist probability, what's called a frequentist probability. All you learned about probabilities in your high school are frequentist probabilities. Bayesians basically say, sure, I'll give you a number. Okay, I mean, this is what I feel. My personal belief is Einstein on that day, okay, 0.3 is the probability that he's drinking tea. You're not going to be able to say, no, you cannot disprove me because you can't repeat this experiment either. Do you understand what I'm saying? So if given frequentist probability, which seems to have this beautiful connection to, this infinite asymptotic ratios of infinitely often repeated experiments, and this idea of Bayesian probability, which is my personal probability. For example, a certain person has a personal probability of what happened in the US election, which apparently is different from everybody else's probability of what happened in the US election. So that person is Bayesian. Do you understand what I'm saying? So the question is, given these two theories of probability, which would you think will actually win in the long term? Which do you think people are using a lot of now?
Bayesian.
Bayesian is actually what is being used a lot more. And for the longest time in statistics departments, if you bring up Bayesian probability, you would be thrown out. Because they would just say, this is like, this sort of subjective namby-pamby math. What is this thing? Like, I feel like this is a probability. And if you can feel like anything is a probability, then what are the constraints then? Well, the constraints are the laws of probability. Do you understand what I'm saying? You can't have, if I ask you what's the probability of A, and you may have some number, what's the probability of B? You may have some number. What's the probability that A and B occur together? You may give some number. Then now if I ask you what's the probability of A or B, you don't get to give a different number for it. You have to actually use the formula. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. You guys remember this? Some of you who remember probability theory? It turns out if you don't use it, then you might say, hey, come on, you're letting me be, less is fair. I mean, I get to make my own probabilities up. You're letting me make probabilities for probability of A, probability of B, probability of A and B. Why can't I also make probability of A or B? Do you understand what I'm saying? And it turns out that if you were to make that number 2, then in essence, I can, it turns out that I can create a gambling game which I will play with you. And if you don't believe that probability of A or B is equal to probability A plus probability B minus probability of A and B, then eventually I will get all your money. The gambling game will be such that you will lose all your money by taking part in it. So this is where it catches with you. So in essence, that's the what's called definitist argument for why probability of A or B should be. So there is freedom with restriction. Do you understand what I'm saying? There's freedom. You can make up some probabilities, but there is some loose restrictions about how those probabilities should be combined. Now, having done these probabilities, these personal probabilities this way, then the question of being rational is whether your decisions are consistent with your own beliefs. Do you understand what I'm saying? There's nothing wrong in you thinking that right now it must be raining outside. You're sitting inside, I mean, except for this girl who's sitting nicely under the tree. She knows objectively whether it's raining or not. Rest of you are all stuck inside. So you could believe, I'm pretty sure it's raining outside. So if I ask what's the probability it's raining outside, you could say, I feel like saying it's 0.7 or maybe 0.9. Okay. Then I say, let's all go out respectively from our rooms to outside. And when you get up, if you don't take an umbrella with you, or when you get up, if you don't take like a raincoat with you, then I'll say you're being inconsistent with your beliefs. If you really believe that it's raining outside, how come you're not taking an umbrella? So that's basically irrational to believe. So it's like to believe that the world is going to end tomorrow. Okay. And then buying a lottery ticket, which will actually, the lottery will be known only next week, is inconsistent. If the world is going to end, then what is the point of buying a lottery ticket for next week? At least you should be consistent with your stupid beliefs. That's all Bayes says. That's all basically AI says. And if your beliefs are closer to how the actual environment works, then your performance in the environment might improve, can be improved. I don't know whether you guys are confused enough with the circularity here of the levels of personalization. So for example, can somebody take this example of you thought it is raining outside, and then you decided, when I said, let's go out, you decided to go out, but without taking umbrella. And then I say you're irrational. Can you tell me how they may actually not be rational?
They want to get wet.
Yeah, exactly. That's their reward. Do you understand what I'm saying? They like to want to, I mean, so basically rest of us seem to have this generic reward function that getting wet is something bad. They think that, you know, the entire, I mean, they're actual native Arizonans. They are like totally parched for rain. And they're saying, finally, it's raining. Why the heck would I take an umbrella? Do you see what I'm saying? If they also say, we don't want to get wet and we believe it is raining, then I get to say you are irrational. Do you see what I'm saying? Okay. Anything else? I mean, that's actually crazy. That's crazy stuff, but that's reality. It turns out that's basically, there are numbers and these numbers are coming in particular when you have humans in the loop. These numbers are rewards you're associating for people. And if people don't think that's a reward for them, then it's not going to necessarily work out well. Anything else? Yes.
This kind of a short sentiment, but when you're talking about how people would rather have like interact with people who are not rude but incorrect, I took another honors class and it was about the science of compassion. When we were looking at studies, you're more likely to get a complaint or like malpractice if you're rude and not necessarily the procedures that were done with the patient.
Mm-hmm. Yeah, no, I think that's the thing, that the whole bedside manners, you know, in US medicine. Okay, I mean, actually, I should give you this example. This is unfortunate because I'm old and I have too many examples. So my father, in 2015, yeah, had an open heart surgery in California. And my sister is a pediatrician, so she has very good connections to, you know, Kaiser Permanente. She's in Kaiser Permanente. So we had to figure out who is the right surgeon to do this particular you know, surgery for my dad. And she found out that there was this one guy, you know, a Vietnamese man, you know, who is considered the best in terms of cold hard statistics, in terms of the number of open heart surgeries this man has done, and the number of them that were successful in the sense that the patient survived for a long time. But they also said that this guy has pretty bad bedside manners. Okay, bad in the sense he was indifferent. He basically said, why do I need to put up this I care about your life thing? I'm supposed to do good job of doing you know, surgery on you. So in fact, it was completely true. It was like hilarious almost. If we went to him without knowing beforehand that he was objectively the best heart surgeon, we would not have picked him. We would not have picked him. And in fact, the funny thing was, after this surgery was done, we were all waiting outside. You know, this is a complex surgery, open heart surgery. And he comes out, and normally the surgeons are supposed to come out and say the surgery went well, and, you know, sort of commiserate with you and try to tell you how things are going on. So he just came out and he said, yeah, surgery went well. There were more things that were problematic, so we had to cut off more things. It's fine. Any questions? I kid you not. This is exactly what he said. Okay. And it was like hilarious. He's like probably the worst bedside manner doctor that I have seen. But honestly, what are you trying to optimize for? So to some extent, you know, in fact, unfortunately, in the US medical schools, we do actually ensure that the bedside manners are given higher priority. So sometimes the people who have better bedside manners but are actually pretty bad in their raw performance on the particular surgery. You know, I understand that bedside manners are extremely important for counseling. If you're a psychiatrist and you have a bad bedside manner, that's the only thing you do. right? What else is left? But on the other hand, if you're a heart surgeon, like when I'm actually doing the surgery, you're not even there. My dad's basically his entire body is being run from outside when he was completely sedated and they were essentially doing the surgery on the heart. So why do you care whether I spend my time trying to be nice to you or I spend my time trying to do the job right? So that is where actually, because we always like good bedside manners, no matter what, we might actually do things that are irrational for ourselves. I mean, that are not necessarily best for ourselves, because we might well pick things that have the right effective. This is the same thing I was saying, that two people, one person gives you the right help, but with a smug look. The other person gives you the wrong help, but, with very sympathetic look. We go for the sympathetic person in the beginning. And then after a while, you will realize this is not going to work. Okay. Anything else that you wanted to bring up from that? So most of you hopefully watched the pieces that I said you should look at from that last lecture thing, because you notice that some of the things we were talking about last class plus more were discussed there. Anything else that was worrisome or concerning or you had questions on? Yes.
I had a question, but it's not about the videos.
Okay.
So this morning, I saw on Instagram, ASU had announced that they were planning on putting in the dining halls like AI trash sorters. That like when you walk up to it, it would like scan like your trays, like assuming in-person dining comes back anytime soon.
Mm-hmm.
It would scan your tray and it would let you know which either compost, recycle, or trash your different items have to go into.
Mm-hmm.
And so I was like reading up about it earlier today just to try and like see how it's able to scan it. So I just want to know, if you have a very full tray, how would the system be able to scan the full all the items so it could correctly tell you which
object segmentation. So first of all, image recognition has become AI right now. If you recognize an image, then it's AI. Do you see what I'm saying? So we are currently going through this scenario where when they say AI is behind it, that means it told you this is a banana, this is an ostrich, this is a school bus. Okay. And similarly, this is wet stuff, this is dry stuff, this is paper, this is utensils. That's the kind of thing that you need to do to separate trash out. So when you have like a bunch of objects together, current technology is such that you can do object segmentation and recognize the objects in the picture. But having done that, the recognition has the usual brittleness that we talked about, like, for example, school bus becoming ostrich. But most of the time it works fine enough. And so you could use it as a basis for this, especially in trash compacting, right? Because it's not going to kill anybody. At best, ASU dorm hall might throw some steel forks, some forks into the recyclable, forks into like the organic material, thing. It's not the end of the world. Okay, so the failures basically are the robustness. I mean, the failures are not high cost. So that's where I would use this kind of image recognition. Okay, certainly as to how you actually pick the different objects in a scene, I mean, that's sort of a little bit beyond what we have done here, but essentially most of the approaches almost do brute force. They look for essentially split the picture in front of you into regions which are progressively grown. So in fact, one particular idea is this idea called labeling every pixel with a category. If, for example, I have a plate with an apple here and some orange juice here, let's say, and like a piece of bread here, then when you take the picture, then there's like a region of the picture has appleness, because those are all pixels corresponding to apple. Okay, and there's a pixels corresponding to orange juice. There are pixels corresponding to the bread. So one of the things they'll do basically is there are techniques now which will label each of the pixels as this is an apple pixel, this is a orange juice pixel. And you go from there to say that if there's a region of apple pixels, then it's apple. Okay. That is doable. That's very much, is currently doable right now. It's funny though, that as to what you have to do to say AI inside, essentially any image recognition has become AI inside right now.
Yeah, I guess I was just wondering, because I know, like, for myself, when I go to the dining hall, there will be times where it's like, if it's the first time I'm eating, I'll grab like a lot of boxes of food. And so I was just wondering, like, I guess if you have stacks of stuff on your tray, how would it be able to recognize everything?
No, it's not that way. I'm pretty sure it hasn't yet started, right? So they are going to probably tell you, they can very well take pictures of each tray separately, that as the minimum. They can't very well look at the entire stack.
It's a company that's been doing this for a few years now at other college campuses, and they're just bringing it to ASU. It's not an ASU developed thing.
Okay, yeah. No, but I'm pretty sure they will basically make sure that each of the trays will come separately. Most of them have this busing thing, right? So you put them on the bus, and so it's slowly passing by. There's a camera that can take a picture and then use that. I mean, it's not that I can do it like in the next couple of hours, but I can see there's nothing theoretically stopping that from being very much feasible right now, given the technology that's there. Anything else? Okay, so let's change track and try to do a few things like last time about, let me see if I can do this. Give me a second. Okay. 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 Let me give me a second. Okay, good. Okay, so let me walk you through a few things like what we did last class, so that it's more me teaching you a few things, actually including, let me actually just get out of this. This is the one that you looked at already. Let's not look at this. 6, right? Oh, there. Okay. So we're back to our old stuff. And, I want to say a few more things with respect to this and then do a couple of things regarding machine learning too. So this is where, okay. So this is where we stopped last time, right? The idea that the agent did not know what was there here and here. It didn't know that these states even existed. And so the question is, if it only knew the rest of the states, it could potentially make an optimal policy that will forever doom it to never finding these states. And if it doesn't find those states, it is possible that those states are high reward bearing states, which is what was a clean way of seeing why exploration is important for a reinforcement learning agent. That was the whole discussion that we had as to how do we get the agent to explore. So in fact, the interesting thing is human kids in particular, evolution has essentially made sure that we have this exploration bug. Kids, not the old peeps. Old folks basically say, just leave me alone and give me my candy and I want to live my life. When you are a kid, all of you are great scientists, right? Because if not, you would not have figured out how the world is working. You were exploring, you basically didn't know anything about the world. So you were in full exploration mode, full on exploration mode. And if you did not explore, basically, you would not get to the stage where the rest of the humans are, who have some idea about how the world around them works, which is basically what kids do in terms of playing with everything. The word play is exploration. They're trying to figure out, oh, this is what happens when I put my hand on the red hot stove. Oh, this is what happens when I push this thing off the table. Do you see what I'm saying? So that exploration is basically in itself a reward-bearing thing. So they will actually do it anyway. For our artificial agents, you need to make them do this epsilon optimal exploration, which is 1 minus epsilon fraction of the time, do what is the optimal policy with respect to what you know. And epsilon fraction of that time, do something random. Okay. And as long as you do that, essentially, you are guaranteed asymptotically to find the true optimal policy of this little world that I know fully. You only knew these pieces, the ones in this part. You only knew these pieces. But as long as you do exploration epsilon% of the time, asymptotically, that means before the universe ends, you would have figured out the full state of the world. And you could then have figured out the optimal policy with respect to the full state of the world and full state space of the world. Okay, so that basically, so as the point I was making last time was the difference. First of all, we talked about MDPs. MDPs have this notion of this is a model. This is called the transition model. It is telling you how actions get you from state to state. And these numbers here, these are called reward model. If I give you both the transition and reward model, then you can compute the optimal policy, which is basically what we talked about most of last time. And then I said, you may not know these models, this transition model and the reward model. So then you, by working in the world, you will slowly learn the transition as well as reward models. Okay, that learning part is the reinforcement learning. Okay, but whenever at any given point of time, you have some idea about the state space with respect to which you can then compute the optimal policy. And that's what you would be doing as long as you believe that is the only state space. But since you are not sure, you essentially epsilon per fraction of the time, you would be doing not what the action, what the optimal action optimal policy set should be the action in that state, but something random, epsilon % of the time. Now, this is just a simplest idea. There are better ideas. For example, you can start by changing epsilon as you live longer and longer. When you were a kid, epsilon was close to 1.0. Because all of it, you did know nothing about the world. So exploration was a lot more important. And as you become older and older, you might say, I know enough about the world. I don't want to explore anymore. So you make epsilon lower and lower. So you can change epsilon over the time of the agent's life. Okay. So that basically says you reduce your exploration as you grow old, which is really depressing. But, you know, if you are all the time exploring, and if you happen to have family, most people who all the time are exploring won't have a family, because basically they are just doing random things all the time and they cannot actually put on roots anywhere. But if you do have a family, they will say, you know, come on, settle down, you know, start making some money by doing some Python hacking. Okay. So that epsilon, there are other reasons why you might actually reduce epsilon as time goes on. As long as it never becomes 0, there is a theorem, I mean, I can prove that any agent which doesn't make epsilon, the exploration probability 0, will eventually learn the correct model of the world, and so it can then optimally make the optimal policy for that world. It may very well be that that'll happen. It only happens asymptotically, in the sense if you give infinite amount of time. So you might still die because you guys don't seem to live beyond like 100 and something. So you might die without having figured out all about the world you live in. Most people do actually. But as long as you have epsilon non-zero, then at least theoretically, there is a hope that if you live long enough, you will figure out all about the world. One very interesting thing with respect to this, if I can actually, one very interesting thing with respect to this is, I wish I quit myself like a, okay, let me do this. I'll get out of this. I would go here. Okay, so I'll write this here. Exploration, exploitation, trade-off, right? That's what we're talking about. How many of you have gone to Las Vegas and played those slot machines? Okay, so the rest of you are more like me. I get no satisfaction from playing slot machines, but some people actually get happiness by playing slot machines. That's why Las Vegas exists, right? Okay, so it turns out that a slot machine is also called what? Do you guys know what it's called? It's called a one-armed bandit. Right? Because it has a one arm that you pull and it basically takes all your money away, right? If you haven't figured this out, essentially, I mean, Las Vegas doesn't exist to make you rich. On average, they have to make you poor and they have to make themselves rich. And in fact, people have said that all gambling, including lottery, has been said lottery is a tax on stupidity. Right? Whenever you buy a lottery ticket, tell yourself that, okay, I'm paying my annual tax on stupidity, right? Because we have this, you know, like the Messiah complex. Everybody else are just giving the money. I'm going to get the money because I'm special. Okay. But anyway, so gambling, one-armed bandit, right? So the question, the question is, if you just walked into the, one of these gambling houses gambling halls in Las Vegas, right? You have to figure out essentially how to play these things. Right? What people try to do is they'll try to pull this a few times to see how often it seems to be giving money. And they'll try to make some kind of a probabilistic model of how often this thing gives money as against mostly taking money. And having figured out the model, then you can exploit it. Do you understand what I'm saying? So if you are playing one-armed bandits, you would be doing reinforcement learning on a very simple one decision MDP. Just one decision. It has one state. It has a one action rather. One decision means one action MDP. The only action you have is pulling the arm. What you're trying to figure out is what is the probability. Remember, when I tried to go this way, my action, if I go up, it was going up 0.8 probability, going right 0.1 probability, going left 0.1 probability. What I'm trying to figure out is if I pull the arm for this machine M1, clearly it is with some probability P, it gives me 0. That means it takes my money. And it is probability 1 minus P, maybe there are different ones. 1 minus P, it'll give me some money. And it can also give different amounts of money. Sometimes it'll give more money, sometimes it gives less money, etc. So there are outcomes, and you're trying to learn this. Okay, have you seen these things where, I forget which was the movie or something, I forget, where these people will be hanging behind you when you are in the gambling hall, and as soon as you leave, they start playing with the machine. And basically, it seemed to be those of you who are crazy enough to do this, and like it, you do know that those are the evil people. In fact, you should, shoo, go away. This is my machine. You're trying to just somehow, I'm trying to learn the model, and just about after I learn the model, I'm going to get more tokens, and you will then pull the thing and you'll get all the money. Because you're sitting behind me and watching how this machine is working. Okay, so in fact, it turns out that the reinforcement learning, the fruit fly of reinforcement learning is Bandit Problems. You know what do you know what I mean by fruit fly? Fruit fly is basically like biologists deal with fruit fly because it is the one with the simplest kind of genome. And so they could do interesting, if you can figure out how fruit fly works, then you might figure out, to the extent you have this overarching hypothesis that genetics works the same across all creation, not creation, sorry, extremely sorry to say the word creation, all the living things, right? If you figure out how genetics works in the fruit fly, then you can then try to use it for understanding how life works anywhere else. And so bandit problems become the fruit fly of reinforcement learning research. Okay, and bandit problems are the simplest form. So you might think that this is actually much simpler than the grid problem that we looked at last class, right? The grid problem we looked at is way more complex than the bandit problem because it has many actions and you have to sequence them together. You thought that was a simple problem, but a lot of theory of reinforcement learning is actually done with respect to bandit problems. Okay, I wanted to mention that. And so in fact, they actually, there's issue. So in terms of the bandit problem, given you have a certain amount of money, how much of this money are you going to spend trying to learn the model of the bandit? And how much are you going to spend in exploiting the model you learned to make big bucks? That is your exploration-exploitation trade-off in the context of bandit problems. Okay. There is an entire cottage industry of bandit problems, like one armed bandit I mentioned. So you can have multi-armed bandits. That means there are multiple slot machines that you're trying to. In fact, some people who are crazy enough, maybe one of the two people who said they actually don't play with just one. They'll put money in like 3 or 4 machines and see how these things are working. And there is this nonsensical, thing like the hot hand. This particular machine is just about, it's like bursting to give me money right now. So I'll play more of this. This is all your way of figuring out the model of the machine. And behind the scenes, the people running the gambling house are looking at you and say, we're getting all your money, right? But that's basically what you do. You're trying to learn the model and exploit it. That's one part. The other thing I want to get across is we showed this, right? We showed this kind of a picture before. And I said in most of what I showed was that I showed that, optimal policy comes like this. So in this particular case, this is like an optimal policy. And look, it sort of makes sense. Okay, this one sort of makes sense. I also tried to explain to you that these policies for very different rewards sort of make sense. So what I want to tell you is, how did I compute the optimal policy? How did I actually, compute this? Okay, I'll give you a simple idea that is actually quite deep, and it's basically a variations of that you would do for even more complex MDPs. So here I will look at deterministic version again. Deterministic MDP. That basically means if I try to go up, I'll go up with 1.0 probability. If I go right, I go right with 1.0 probability, unless I hit the wall, in which case I stay in that room with 1.0 probability. Deterministic is nothing but stochastic with ones and zeros probabilities. It's a special case. Okay, so assume this is the kind of thing, and this one, if you get here, you will get +1. And remember that in any state you will get minus 0.04 units penalty. I'm trying to figure out what action should I do in each of these states. So what I would say is, let's do the following. So this, if you are here, what is the maximum you'll get? +1, and then you die, right? Because that's the nirvana state. If you are here, what is so basically I could say the value of this state is +1. Do you understand what I'm saying? The value of this state is +1. Value is different from reward. And keep that in mind. It's actually extremely important. This is very, very important. I'll explain to you why in a minute. But suppose you are here, just intuitively, what do you think is the value of this state? I would say the following. Well, you're like very next to this very rich guy, +1. So if you basically do an action from here, the right action from here, which is going right, you will get the +1. Right? But since you are stuck here, doing that action, in essence, you are still stuck in this current state. Really, it's 1 minus 0.04. Right? That means this guy's value is 0.96. Okay. By the same argument, this guy's value also would be 0.96. Agreed? Now what will be this guy's value? This guy can essentially go to either this guy or this guy, and then from there he can get to the goal. So this guy's value will be 0.96 minus 0.04. So 0.92. Do you see what I'm saying? Anybody has any worries in figuring out what I'm doing here? I'm just doing a backward sweep of the values of all the states, starting in this particular case because there's a goal. Okay. And then now, similarly, because this is 0.96, then this will be 0.92. Because this is 0.92, this will be 0.88, right? Because of this, this will be 0.84. What is the value here? I would say you can't right away write the value here yet. Because you know, if you're here, you go this way, you get a 0.84 value. But you don't know what you will get if I go here. So I get those two. This is 0.96, so this will be 0.94 and 0.92, because of which this will be 0.88, right? Because of which this will be 0.84. At this point, I know that I'm here. I have two neighbors who are equally good. So I can basically say my value would be 0.84 minus 0.04, 0.80. Okay, this is the idea of value function of the MDP. Value function of the MDP. What do you really want to do? You wanted the optimal policy, but I gave you the value first. But can you convert the value into policy? Yes.
Just go to the higher.
Exactly. Remember this, It's a Wonderful Life. How many of you have seen this, It's a Wonderful Life? You will be made to see it anyway. Christmas is coming, right? What do they say? No man is poor who has rich neighbors. I don't know, they don't say it that way, but essentially, as long as you have people who can help you, you're not poor, right? So in essence, what we'll say is everybody looks around and sees who is their richest neighbor and takes the action that gets them through that richest neighbor. Do you get this? So yeah, 0.96, this guy can go this way, this way, this way, or this way. If he goes this way, he will stay in this. So it will be 0.96 minus, because you did this extra action, that's another 0.04 penalty. If you go this way, you'll get 0.92 minus that penalty. If you go this way, it's another 0.92 minus this penalty. Whereas if you go this way, it's +1 minus that little penalty. Of all these four action choices, which has the best value return? Obviously, the one going right. So I will, oh, I'm sorry. Wait, why did I not get this yet? Remember, I wrote this 0.92, 0.94. Okay. And then this is the action here. And similarly, this or this, either of these are the actions here. This is the action 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 here. This or this is the action here. This is the action here. This is the, I'm sorry, this is the action here. This is the action here. Okay. So I computed value first. Then converted into policy. This is pretty much what MDPs do with a little more, here it's deterministic, so it was much simpler. Had this actually been a stochastic scenario, then I would, even as I'm coming backward, I have to compute the expected value for each of the actions. Expected value means the probability P times the value that I will get by doing that action. Okay, it's much simpler to understand in the deterministic case, so I just did the deterministic case. So expected value means weighted average. For if you do an action, it can either take you to S1 or S2 or S3 with probability P1, P2, P3. Then I take P1 times value of S1 plus P2 times value of S2 times plus P3 times value of S3. That is the expected value I get. Okay, it'll become a little more interesting there, but really this is called value computation. This is called policy computation, converting the value into policy. And it's extremely important to realize the relation between reward versus value. Reward versus value. You have to realize that the value of a state, so here's my question, is the value of the state proportional to its reward? Is the value of the state proportional to its reward? You know why this is interesting? Why you want to understand the reward versus value? People who don't want to think can only experience the reward. What's the reward of being in college? Especially this semester when you can't even go to bars. Looks pretty darn negative. Why are you here? Because you're not trying to maximize reward, you're trying to maximize value. Do you understand what I'm saying? You're here because you're thinking somehow, I mean, assuming some traditional model, you are, trying to get some $1 million job. And, somehow you heard on the grapevine that they don't seem to be hiring high school dropouts for these $1 million jobs. So you are sticking by this negative reward experience for the big payoff. Do you understand what I'm saying? So you need a brain which can do computation to realize that the immediate reward is not in any way proportional to the value. You can make examples where the current state is way more, so it looks like a high reward of the two states, like for example, going to the college, like coming to this class right now versus watching something on Netflix. Clearly Netflix, plus 3.0 reward. Coming to this class, minus 7.0 reward. Right? Okay. So the point is I can make states in such a way that basically the reward, immediate reward, has no connection to value. You have the brain to figure out how to convert reward and the actions you have into the values and use the values to make your decisions. Do you understand what I'm saying? So this business of computing using my action model, right? Using my action model and the reward model, I was able to convert it into actual value, which I then was able to convert into policy, optimal policy. And the optimal policy is actually not at all connected to the reward, because if you are looking at rewards for all these states, they're all indistinguishable. In this example, they're all minus 0.04. And you had no idea which way to go, but the values told you which way to go. So that's what your brain is for, computing the value from the rewards. But suppose you don't have brains, or suppose you don't want to use your brains, and I still want you to succeed. Like, for example, I know Homer will become civilized if he were to go to library. Homer will not want to go to library, even though he will become civilized if he goes there. Right? So what do? I will put pink donuts lining the street all the way to the library. And Homer will then follow the trail of the donuts. And then we'll reach the library, we'll reach nirvana of being civilized. That part is called reward shaping. So I'm saying two different things, and I hope you are getting it. One, reward is not at all connected to value in general. And if you don't have much of a brain, you will do the greedy thing, which is, looks like this is sweet. It should be good for me. Eat more of it. So you are maximizing your immediate reward without thinking about the value. Do you understand what I'm saying? But I want you to actually do the right thing despite your inability to do reward to value computation. I will change the reward of the state. Why is it that all medicines are sweet? Do you think about it? Medicines are good. You think juniors will take medicines that are bitter? No. Do juniors have brains? Yeah, kind of. They mostly don't do long-term reasoning. So you sugarcoat the medicine. And then the junior then you have to stop the junior from eating too many of them because they think it looks like candy. But at least they will take, like, what is the point of the flavor of Tylenol? Who the heck cares? Does the pain centers care about what flavor of Tylenol they're being inundated with? No. It's the agent who is putting the Tylenol in the mouth doesn't have the ability to think about value. So you reward shaped. To make people do what is right for them despite their inability or uninterested, they're not interested in thinking for themselves, you actually shape the rewards of the states. And this is also basically called incentive designs. Mechanisms. To understand this, you have to realize, really, you don't need to design incentives. Kids, if they have working brains, they should be able to realize that taking the medicine is good for them. students, if they have brains, should realize going to college is good for them. Neither of them do that. So in classes, I have to tell jokes just so that you'll feel good, at least instantly. And for medicines, I have to make the medicine sweet so that the junior will eat it. So you're making the greedy policy that people will use. The greedy policy an agent will make will be the one that picks the high reward state. The reward has nothing to do with value. Okay. So in fact, the way we computed this value, this is basically in computer science, it's called dynamic programming. You don't need to know this except you are a computer science geek. And then many years later, when you're taking algorithms course, you will hear dynamic programming. You better remember that Rao one day said this. Okay, so you're using this nice backward pass, computing the values. Actually, it turns out that if you don't want to do dynamic programming, you can do something else, which is initialize everybody's value to some random number. Initialize everybody's value to some random number, except this guy, because this guy has a real value. It's not, you cannot change it. Because this guy's reward as well as value is the same. Right? Because you get to that state, you die. So you get a +1 and you die. So for everybody else, I can initialize the values to be some random numbers. Then each of you look around your neighbors and change your value based on the neighbor who is the richest. And you do this in waves. You know what will happen? This guy, irrespective of whatever number you gave this cell, in the first iteration, he'll realize, okay, I have some random loser guys and like a +1 guy there. And I'm not stupid. I know that I can do an action to get to +1. Why would I care about my loser neighbors? So I will just change my value to be +1 minus 0.04. In one iteration, I got my right value. The people here, they're still essentially looking at their random neighbors and picking the random neighbor who is slightly better. In the next iteration, because this guy has the better correct value, his neighbors or her neighbors will get their values better. Do you see what I'm saying? It's like that, there is a rich person, the neighbor surrounding basically say, hey, we found a rich person. And in the next iteration, everybody will say, hey, these guys found a rich person. So let's follow these guys. And then the message passes. This idea is called value iteration. Value iteration. The next time you hear it will be in 471 or some reinforcement learning course. This is what we're doing. This course is a wormhole in your program. Right? You will hear things here and then you will hear it again after 4 years if you're only going by courses. And it turns out that value iteration works. So I don't even have to do, all basically I need to do is I look at my neighbors and update my value based on my richest neighbor. If I have stochastic actions, I look at my neighbors and for each action, I compute the expected value because each action might take me to 2 or 3 different neighbors with different probabilities. So I do the weighted average and I say, oh, so if I take this action, this is the value I get. I take this action, this is the value I get. I'll take the action that gives me the highest value. And then that would be my way I'll change my value. Okay. And if once you do value iteration, you'll get the value, at which point of time you can convert into policy. And some of these ideas are not that different from what things like AlphaGo use, if that catches your attention. Okay. Any questions on this? Remember, this is what I did end of last class for the 1 hour, and I assumed that there would be, you'll cry bloody murder, but this is the class that that's the part that most people seem to have liked. In fact, everybody said, whoever said feedback said it was great. So I'm doing more of it. So I basically, now I figured out your reward metric. So I'm going to sort of, you're masochist, so I will serve your masochism. Okay. Any questions on the previous one? Okay, let's do more wormholing. Remember this whole thing that we did? We did MDPs, we did reinforcement learning, we did computation of policies, we did computation of values. With all that, the robot, the environment that we are looking at, was it static or dynamic? We looked at this, say it loud. Is this static or dynamic environments we were looking at?
Dynamic or static dynamic?
Static. There is no other agent, it's static. Okay. Is it deterministic or stochastic? We considered both. The version that we are looked at today is deterministic, but we also looked at stochastic one. And stochastic, you just take the expected value back up. By the way, you guys do understand, how many of you know the word expectation? Suppose with probability 0.7, you will get $400. And with probability 0.3, you will lose $100 in this gamble that you're taking. What is your expected reward? Expected backup? It's 280 with this, because this 0.7 times 400 plus 0.3 times minus 100. Right? So that is 280 minus 30, 250. That's expectation. Okay. So what is happening actually when you are doing stochastic action? So basically, this agent was doing a stochastic action with 0.7. The agent will go to a state with 400 value. With 0.3 probability, the agent will go to a state with minus 100 value. So then the agent realizes that what I'm getting here is really 250. The expected value is 250. So here the agent is playing against the nature. Stochastic action means it's a game with nature. And I asked you, would you rather play with nature, or would you rather play with your enemy, a human being? Would you tempt fate or tempt your enemy? Any day, tempt fate. Because tempt nature, nature doesn't even care that you exist. It's not out to get you, it's not out to make you happy. Your enemies want to get you. Your friends want to make you happy. So in the case of games with nature, you will do expected value. Imagine it's the same thing where you are playing chess. There is a great move. Okay? There is a great move. It can either lead to a 400 value or a minus 100 value, depending on what the opponent does. What do you think is rational for you to expect as the backed up value here?
That the opponent does what's best for them. And
Which means, assuming that it is a zero-sum game, that's another name.
then that's worse for you.
Yeah. So you take minimum of these and back it up and say, oh, looks like this guy will give me -100. And suppose there is some other action here, another action which has one side 200, another side 5. Then that guy's minimum backup will be 5. Then I need to decide between these two actions. This will give me -100. This will give me 5. So I'll take max of -105. Did you just see what I said? And this is called min-maxing. When you have an enemy, when you have an opponent, your deep blue, your AlphaGo, all of these play min-max search. Do you see what I'm saying? Because when you have an opponent, you should assume they're perfectly rational, because that's a conservative thing to do. And so you take minimum, at the level where it is opponent's turn to make the move, and maximum at the level where it's your turn to make the move. Min, max. On the other hand, if you're playing with the nature, you do expectation, maximization. Instead of min and max, you do expect, max. So that's what is called expectation, expect, max strategy, which is basically what you do if you're a single agent playing against nature. Stochasticity means the nature is the other agent, but it's an indifferent agent. It doesn't really care about the fact that you are out there. Okay. So you can actually go from MDPs to chess playing programs with just one little change, which is instead of, if it was a chess playing program, instead of taking what is my maximum or the expected maximum, I have to take the minimum, because I assume that the opponent will try to do the maximum damage to me. In a chess playing program, it's not just you walking through the the maze. The opponent might be changing, for example, the rewards of the states, for example. Okay. So deterministic and stochastic we looked at, and I just threw in as a side bonus, playing with nature versus playing with enemies, min-max versus expect-max. Again, something you'll only hear when you take AI courses. The other question is, are the goals simple goals or general goals? Actually, the goals are general, because I'm allowing arbitrary reward metrics. Every state gives you a little reward and you add them all up somehow, which is what you're doing. About the only thing that we haven't yet considered is the problem observable or partially observable? In every scenario, whether you looked at reinforcement learning scenario where the model was not known, or deterministic MDP scenario where the model is known and actions are deterministic, or the stochastic MDP scenario where actions are known and they are probably stochastic, you still know which state you are in. So everything we have done till now is what is called, in fact, you call them MDPs, but really you should call them form DPs. Fully observable Markov decision processes. Which makes me wonder, what about POMDPs? Partially observable Markov decision processes. Okay, it's a harder class of problems. Your life is actually more of a POMDP than an MDP. It's actually reinforcement learning on a POMDP. Your life, even if everybody else disappears, is RL on POMDPs. Because you don't know where you are, because you only have partial observability of the world. So a classic example is here. This is the same maze. If it is not observable, that means I don't know which cell I am in. I'm blind, for example, so I don't know which cell I am in. Can I solve the problem? And in fact, notice the following. I mentioned this earlier too, that if you have good eyesight and your friend is partially blind, then what is a POMDP for you is a POMDP for your friend. And so if both of you reach the same level of performance, then you should basically be ashamed of yourself, because, not ashamed necessarily, you should be really appreciative of your friend, because your friend solved a much harder problem to get the same value. Because not seeing the world means you don't know which state you are in, and computing the optimal policy becomes much harder. I want to get you to understand that before we leave today. So in this picture, if you don't know where you are, what does that mean really? If you know this is the world you live in, and you don't know where you are, I would argue that you have a distribution over states, probability distribution over states. That you basically are equal probability that you think you are in any of these states. See, blind people understand. It's like, you know, this stupid thing about we tend to talk loudly to blind people sometimes. They only can't see, they can hear. Okay, so they also can basically understand the problem. I told them this is how the grid would be. You just don't know where you are in the grid. So they know that if they were in either of these places, they would have already reached nirvana. And they would know that they can't be in this place because I told them this place is impossible. So unlike you, where you would know, oh, I'm right here, that means probability of this state is 1 and every other state is 0. Every other legal state is 0. If you are blind, you would think all of these are essentially 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/9 probability. Each state is 1/9 probability. So what you have is not state, you have a belief state. A belief state is a probability distribution over states. Okay? How do you think you work in this kind of a scenario? What do you do when you wake up in the middle of the night in a strange place where you just happen to see the room before going to sleep once, so you don't know very well, you know approximately where the big obstacles, etc. are. And then you woke up in the middle of the night, you need to go to kitchen to get some orange juice or something. What do? You don't want to put on the light. Suppose there's no light, or you don't want to put on the light because you don't want to wake up people. What do you do? You need to find where the door is. How do you do it? To figure out where the door is, you need to first stabilize yourself. You need to know where you are so that you can go to the door. Do you understand what I'm saying? So when in situations like this, a blind agent, a non-blind agent knows the goal, knows where they are. They just need to go to the goal. A blind agent first needs to do some actions to figure out where they are, and then use that knowledge to go where they need to go. So here is the idea. The belief state in this particular case is 0.111 for all of the states, right? Imagine the following thing. So imagine that you are in any of these states. You don't know where you are. You are in one of these states. You are really like the Schrodinger's cat in all these states with these probabilities. Okay. Imagine you decided to move left 5 times. Just move left 5 times. You can't see, but you can do. You just move left 5 times. What happens? You hit the wall. This is what you're supposed to do, by the way. If you wake up in a strange place, you try to make a beeline to the wall and then follow the wall to get to the door. Which is why, how many of you know Helen Keller? And the mean joke about Helen Keller is that her mother made her room cylindrical. Because then that means there are no corners. So poor Helen will not be able to still figure out which way to go. But in general, getting to the wall reduces the uncertainty about your state. That's what you're trying to do here. With the exact model we had, where going up will be 0.8 going up, 0.1 going right, 0.1 going left. Remember that model? If you do that, and if you actually just compute the probabilities of all the states after moving blindly 5 times, this is what your belief state would be. So previously, the belief state, if you have like, previously if you have states 1, 2, 3, etc. up to 9, those are all the only states that you need probabilities for, because the other states can't be there. Previously, a belief state probability distribution was like that. Now, you notice all the wall states, all the left wall states have high probability. Did you see what I'm saying? The left wall states have high probability. Is there uncertainty still? Yes, but there is less uncertainty. So instead of it being like this, you are now sort of more like this. So this distribution has, whoever tells me the right word wins a prize. This distribution has what jargon word compared to the previous distribution? I just threw that jargon last time. I don't expect you to remember, but if you remember, then you get a prize.
Entropy.
Who said that?
Joshua.
Good. Joshua wins a prize. He won't know what the prize is. It's partially observable world. Entropy. In fact, the deterministic world has the lowest entropy because it has all its probability mass is concentrated in one state. Not knowing where I am, the uniform distribution has the highest entropy. Trying to estimate your state by doing actions, you are reducing the entropy of the state distribution probability, the state distribution function. Now that you know where you are, Then essentially, with respect to this, then after moving left 5 times, then suppose I move up 5 times. Okay? If I move left 5 times, that means from this state, I move left 5 times. I move up 5 times. Then all the probability will be sort of concentrated here. More of the probability will be concentrated here. It's obvious, right? Because you could be in either of these, but if you keep going up, if you are here, you will stay here. If you're here, you will go here. If you're here, you will go here, and then finally here. So pretty much all of them finally get here. Okay? And then if you do right 5 times, right 5 times, okay, you would get that. So you have very high probability of being in the nirvana state, which is what you want it to be. This is what blind people have to do. Okay, so if there are n states, how many belief states are there? If there are n states, how many belief states are there? That means how many different ways can I put a probability distribution over n things such that they all add up to 1? And they should all be non-negative, between 0 and 1, and their sum has to become 1. How many different ways can you split the probability between 9 things such that it will add up to 1?
Is it infinite?
Infinite. Now do you have respect for people who are blind? What you thought was essentially a simple 10-state problem has become an infinite belief state problem for them. The interesting thing is we are all blind. We may know where we are in this state, but in the real world, you don't know your full state anytime because there are many, many hidden variables. So really, mostly you will all have to deal with POMDPs. And in case of POMDPs, you will wind up doing state estimation first, which is doing actions only to figure out where you are, then followed by goal progress. Remember, there's this joke that people say, what should I do? And they will say, well, it depends a lot on where you are. Half the time, people don't know where they are. I mean, they know where they are in this particular cell game, the grid cell game. But if you come to me and say, Rao, I want to do research, what should I do? Well, it depends on where you are. Do you know linear algebra? Do you know this? Do you know that? First, you have to figure that out, and you figure out what your capabilities are, and then you figure out how to go. That's it for today. Actually, I also wanted to show you TensorFlow pictures, but I don't think I'll have the time. Actually, let me just show you this before you go off. 2 minutes, okay? Just to get you into thinking about the TensorFlow thing, which we'll get next time. Forget about all this stuff. It's a completely different thing now. What is the next number?
Ten.
10?
I mean,
42.
there are an infinite number of answers, right? But 10 is a good one.
So how did you decide it is a 10? I'm sorry. Basically, these were the points for 1, 2, 3, 4, the numbers were 2, 4, 6, 8. That's all I gave you. I just gave you these black points. And I just asked, what's the next number? And you said 10. Basically, that meant you decided that I believe that the function is a line. Did I tell you it is a line? No. In fact, if I were to fit the best line that goes through all these points, this would be that best line. And according to that, at 5, the number will be 10. So think of what happened here. This is training data. And this is the test question. And you needed to make a hypothesis based on the training data, what the pattern is, and using the pattern, you needed to guess what the next point is. If you're looking for lines, this is the best answer. If I am allowing you to look for any best fourth order polynomial, a fourth order polynomial will be of the type ax power 4 plus bx cube plus cx square plus dx plus j or something, where you're trying to find a, b, c, d, j. The first start, the line is y equal to mx plus c. And you just, using the original points, you figured out what's the best values for m and c. And then you got the line. And once you got the line, you throw in the x, you'll get the y value. If I fit the best fourth order polynomial, this would be that. According to that, it's just as good as somebody was saying the infinite number of answers. It's just as good for you to say that the next number is some 40 something. Both this guy and this guy are equally correct with respect to the training data. They completely agree with the training data. They are, both of them go directly through these 4 points I gave you. Which one would you pick? And if you pick one of them, then you would say you have bias. And it's a different kind of bias. This is the technical learning bias. Because learner is looking for a hypothesis, which is a function type. And among those function types, it's picking the best function type. And one of the big issues is, this is a classic deep problem in machine learning in general. You don't know what the underlying function is. So you just make the line assumptions because that's easy for you. But that's not necessarily the right function. But if you allow much higher order functions, then they will be consistent with any data, even if in fact they are not truly the function that governs this data. So every learner has to make assumptions outside of the data, and which is hypothesis space, and that would be called bias. And one of the very interesting questions is that if you are trying to consider different kinds of functions, classes, and find the best function fit with respect to the data, as you increase the higher and higher order functions, if you take higher and higher order polynomials, the training error has to become lower and lower. If I can fit a line through your points, I can also fit a second order curve through your points. I can also fit a third order curve through your points. I can also put a fifth order curve through your points. That's just definite. Whereas if I increase the polynomial complexity, there will be better and better fit with the data. But the problem is if the data is noisy, that means some of these points are actually noisy. They were not the exact points. I gave you the slightly wrong values. Then this line will essentially look for the best fit line that is slightly off for the training data. Whereas the higher order functions will go through the noise fully. So then what happens is as the functional complexity goes up, the training error goes down, and the test error, that is the error on the actual test data, first starts going down and then starts going up. We'll talk about this again next class, but this is called bias variance trade-off, which is don't break the egg with the sledgehammer. If you pick very high complexity functions, you can always make the training error 0. What you're trying to do is not to make the training error 0, but to make the test error low. Training error is a heuristic towards the test error, but it's a flawed heuristic. If you take bigger and bigger function classes, that means I have one function class, another class which is bigger than this, another class which is bigger than this. The best values of these bigger sets will have lower training error than the best values of the smaller sets. That's just definition of sets. But that might well be because they learned all the errors also along with the data. And so they don't do as well on the test data. This is called bias variance trade-off. This is also called overfitting. Overfitting, you will keep hearing if you're thinking about machine learning, you'll keep hearing it in that, where am I? In that, if basically you can go through all the points. So irrespective of the thing that I have, like for example, if I have points like this, okay, if you give me high enough order polynomial, I can go like this. Training error 0. What if the real reason I got these points was my measurement was slightly noisy and it's actually just a straight line data with noise? Then the guy using this function will fail more often on the test than the guy using the line. How do you know which is the right one? You don't. And you have to live with this uncertainty over the Thanksgiving break. And then we'll talk more about it when we come back next time. Okay? Happy Thanksgiving, folks.
Thank you.
Thank you.
Thank you.
Thank you. Have a nice Thanksgiving.